Good afternoon, everyone. My name is Haiyang. I'm glad to share our work towards diagnosing accurately the performance bottleneck of software-based network function implementation. Softwarization of network functions increases flexibility and scalability of network functions but also brings limited and unstable performance. Performance diagnosis and optimization is critical for software-based network functions. Compared with hardware platform, processing packets in software means complex, running environments and more intense resource contention. Software-based NFs can lead to several significant performance issues. Complicated algorithm design and code structure makes the performance diagnosis more difficult and time-consuming. In order to explore the performance behavior and performance diagnosis, some researchers employ static cost analysis to analyze the behavior of NF under the simulation environment. Others use queue monitoring and flow measurement to identify the bottleneck nodes and NF nodes in the service chain. Both of them cannot perform downgrade diagnosis inside the NF program. Today, developers usually use the general-purpose performance diagnosis tools based on the CPU hardware figure, performance monitoring counter, PMC for short. The typical tools, PERF and V2, have been well used in NF performance diagnosis, since they are easy to use and have low overhead. However, compared with general computing programs, NF programs have their own performance behaviors. NF are required to continuously provide high-throughput packet processing under strict constraints of latency and packet drop rate. It brings new challenges and requirements to performance diagnosis. Are these general-purpose performance diagnosis methods still efficient for NF performance diagnosis? Unfortunately, the lack of evaluation in NF scenarios right now. In this paper, we first rethink the challenges and the requirements of NF performance diagnosis from the perspective of NF performance characteristics. According to the NF performance characteristics, we identify three challenges for NF performance diagnosis. The first one, performance issues of NF are transitive. Queue is a necessary component in NF packet processing procedure. Queuing makes a performance issues for one packet affect not only itself, but also subsequent subtle packets. Besides, performance issues of NF are transitive. Performance diagnosis method should be able to distinguish among the processing of different packets and find out which packets is culprit and which packets are just victims. Therefore, we propose the first requirement, fine granularity. NF performance diagnosis should provide packet-level and function-level performance tracing. The complexity of modern NF frameworks is the second challenge. The emergence of new scenarios has made the functions of NF more and more complex, and the size of code has extended rapidly. The modular architecture, the dynamic libraries loaded during runtime, and inline functions makes it difficult to diagnose. Based on this change, we propose the second requirement, flexibility. NF performance diagnosis should be easy to apply to complex frameworks and able to recognize dynamic libraries and inline functions. The third challenge is unavoidable performance perturbation. Performance data cannot be captured without any extra measurement operations. These extra measurement operations increase the overall resource consuming and competing resources with NF. The performance behavior of NF will be disturbed. To achieve accurately performance diagnosis, the performance perturbation caused by measurement should be as small as possible. Before stepping into our evaluation, we first introduce our experiment environment and evaluation methods. Our aim is to analyze and evaluate the general performance diagnosis methods in NF scenarios. We build a real NF world environment. All the NF instances are running at a high-performance server. Two servers are directly connected via Mellanox high-performance links. We select three NFs, Framework, Night, and Episode Gateway as our target NFs. All of them are built based on Cisco VPP. Both site and traffic patterns are all generated by ClassBench. For two major types of PMC-based performance diagnosis tools, We evaluate two sample-based and two instrumentation-based tools. To evaluate granularity and flexibility, we analyze their principle and perform diagnosis in real NF scenarios. To evaluate performance perturbation, we propose a quantitative indicator, coefficient of interference. Let's start from the granularity and flexibility. First of all, we discuss the philosophy of PMC-based performance diagnosis. PMC is a set of hardware registers that can be configured to track hardware performance events, such as catch misses, with ignorable overhead. PMC provides two measurement modes, sampling mode and counting mode. Sampling mode PMC and kernel sampling drivers construct sampling-based diagnosis tools. Counting mode PMC and the instrumentation libraries construct instrumentation-based diagnosis tools. In simply-based tools, PMC is configured with a threshold value of n. As long as the counter exists in PMC reads an interrupt. The kernel interrupt handler will fetch the instruction address, PMC register value, and call stack information to constitute records, and write the records into the shared memory. User space measurement process fetch records from the shared memory and generate time aggregate performance data. Since the PMC simply is based on the frequency of occurrence of hardware events, simply-based performance diagnosis tools cannot identify one specific function execution. To verify, we use proof to perform diagnosis on firewall. In the picture, each rectangle represents a function. The shade of color indicates the number of performance events triggered by the function throughout the entire measurement period. The up-to-down position represents the function call sequence. However, the left-to-right position do not reflect the function execution sequence. We cannot observe the whole wheel of one packet processing. We cannot distinguish the data of a specific function execution. Simply-based performance diagnosis tools cannot meet the requirement of fine granularity. In the instrumentation-based tools, PMC just continuously counts the performance events. The measurement process constructs measurement probes. The probes are responsible to read the PMC value, record the location and execution information, construct data record. The measurement process uses instrumentation technology to insert these probes into a field-specific position of the target program. The execution of probes and the packet processing are tightly binding. In principle, they are able to identify one specific function execution, but limited to instrumentation technology. Even there are a lot of instrumentation-based tools, only TAU can be directly applied to VPP. Similarly, we use TAU to perform diagnosis on firewall to verify its granularity and flexibility. The probes are inserted into the major functions. In the figure, each rectangle presents one function execution. The width of the rectangle is the execution time. The nested relationships represent the call sequence, and the left-to-right position represents the execution sequence. Apparently, instrumentation-based tools are able to trace per packet processing meet the requirement of fine granularity. However, even we try to insert probe into all major functions, some key processor stages are still missing, such as ACL model, which is the rule matching of the firewall. This is because these models are built in the separate dynamic libraries and loaded after startup and the linking stage. Otherwise, all inline functions are invisible. They cannot meet the requirements of flexibility. Performance perturbation. Performance perturbation cannot be measured without any extra operations. Extra operations will introduce new perturbation. That said, the real data of performance perturbation is impossible to be captured. Most of researchers just use overall overhead to represent the performance perturbation. Some works introduce study case, but lack of generality. We first follow the most popular method. We evaluate the overhead of PMC-based tools. The figure shows the result of throughput in firewall scenario. Instrumentation-based tools introduce higher overall overhead. This is also the reason why they are not widely used. But for NF performance diagnosis, does high overall overhead means large performance perturbation? We run the above NF again, but using the latency as the performance metric, and we find the similarity of performance distribution. We find latency can achieve stable performance distribution as long as the NF runs in the same environment and configuration. As we shown in the figure, even with high overhead, the major characteristic of distribution can still be resolved. Therefore, the measurement result can be viewed as a slowdown of the original performance. In order to make the evaluation result more intuitive, we quantify the latency distribution similarity. We propose an indicator, coefficient of interference, COI for short. For an input packet site, we normalize the latency data with the average latency and calculate latency distance for each packet. The value of COI is the summary of all packets' latency distance. The less the value of COI is, the smaller the performance perturbation is. Based on the quantitative evaluation method, we are able to evaluate the performance perturbation of existing PMC-based performance diagnosis tools. For instrumentation-based tools, TAU is the only one that can be applied to APP. For sampling-based tools, we choose PERF as the example. The HPC toolkit relies on the same PMC sampling driver, and the behavior is similar to PERF. Give the results of all three NFs, and firewall are configured with two different rule sides. Each tool is tested with both of high overhead and low overhead configuration. For all NFs, even running the sampling-based tools with low overhead, the COI is much larger than that of TAU. For all cases, the COI in TAU is only 7.39% to 74.31% of site in PERF. Even with large overhead, the performance perturbation of instrumentation-based method is still relatively small. In summary, we argue that instrumentation-based performance diagnosis is more perturbation-free than the sampling-based ones. In the end, we give a summary of existing PMC-based performance diagnosis methods. In summary, sampling-based methods fail at packet-level performance tracing and have larger performance perturbation. The instrumentation-based method meets the requirements of fine granularity but fail at flexibility. Based on this result, we discuss how to build a hybrid solution that can achieve accurate NF performance diagnosis. For first glance profiling, hotspot analysis with sampling-based tools is the best choice. Most of sampling-based tools don't need any modification to the NF programs. Developers can directly employ them to perform the performance diagnosis, even with little knowledge of the target NF. After identifying the hard functions during the packet processing, the instrumentation-based performance diagnosis tools can be used to achieve packet-level deep performance tracing. Altogether with lifecycle information, we can further obtain the detailed processing progress for each packet. In addition, more efficient instrumentation-based NF performance diagnosis method is required. The existing instrumentation-based tool have a lot of drawbacks. We plan to design a packet-level performance diagnosis method based on modern instrumentation technology, and build well-defined lightweight measurement probes in the future. Conclusion: we focus on the specific performance behavior of NF. We think of the challenges and the requirements of NF performance diagnosis. We investigate general-purpose PMC-based performance diagnosis method. Through mechanism analysis and NF measurement verification, we argue that existing method cannot simultaneously meet the requirements to granularity and flexibility. We propose a quantitative evaluation method for the performance perturbation, and find that instrumentation-based methods are more perturbation-free than sampling-based methods. That's all. Thank you. Do you have any questions?